Euclid Maths, Euclid Maths, Euclid Maths.
Hi everyone, welcome to part 7 of our lecture series on vector differentiation. In this lecture, we are going to learn divergence operator. Enjoy the lecture.
Before diving into the definition of the divergence of a vector field, we have to recall fields. We have already seen what are fields. Fields are of two types, scalar fields and vector fields. They are also called scalar point functions and vector point functions. A scalar field is a function from r power n to the real number system R. A vector field is a mapping f from Rn into Rm, a multidimensional space Rn into another multidimensional space Rm. Throughout this lecture, we consider vector fields f from R3 to R3 only. So in this lecture, our concentration is on the vector fields on R3. Consider a vector field f from R3 to R3. So its inputs are three-dimensional vectors. Select a three-dimensional vector, say x cap. Since x cap is a vector in R3, it can be written as a triplet. X cap equals x1 comma x2 comma x3. It can also be written as x1 I cap plus x2 j cap plus x3 k cap. Such vectors are inputs for our vector field f from R3 to R3 now. Suppose if we take an input x cap equals x1 comma x2 comma x3, then f of x cap sits inside R3. So it is also a vector in R3. So it can be written as f of x cap equals f1 of x cap I cap plus f2 of x cap j cap plus f3 of x cap k cap. It can also be represented as a triplet f1 of x cap comma f2 of x cap comma f3 of x cap in the 3D space R3. Here the entries f1 x cap, f2 x cap and f3 x cap are real numbers or scalars. The functions f1, f2 and f3 are called component functions of the given vector field f from R3 to R3. So f is a vector field from R3 to R3 and its component functions f1, f2 and f3 are scalar fields from R3 to the real number system R. Thus, every vector field f defined from R3 to R3 can be written by using its component functions, say f1, f2, f3 in the form f of x cap equals f1 x cap I cap plus f2 x cap j cap plus f3 x cap k cap. Now let us define the divergence of a vector field. Consider a vector field f from R3 to R3. Suppose its component functions are f1, f2 and f3. Now f can be written as f equals f1 I cap plus f2 j cap plus f3 k cap. Then the divergence of the given vector field F can be denoted by the symbol div F or del dot F. It can be read as the divergence of F. It is defined by div F equals dou F1 by dou X plus dou F2 by dou Y plus dou F3 by dou Z. If we observe, there are three pieces. The first piece is the partial derivative of the scalar field F1 with respect to X, namely dou F1 by dou X. The second piece is the partial derivative of the scalar field F2 with respect to Y, that is dou F2 by dou Y. The third piece or the last piece is the partial derivative of the component function F3 with respect to Z, that is dou F3 by dou Z. If we take the sum of these three pieces, we obtain the divergence of F. So div F equals dou F1 by dou X plus dou F2 by dou Y plus dou F3 by dou Z. We have to observe one fact. The divergence of a vector field is a scalar. So the divergence del dot is a vector differential operator which is applied on a vector field and it produces a scalar field. In our previous lectures, we have seen the gradient operator. The gradient operator is also a vector differential operator. It is denoted by del or nabla. The gradient operator applies on a scalar field and it produces a vector field. So, gradient applies on a scalar field and produces a vector field, whereas the divergent operator applies on a vector field and produces a scalar field. Pulling together all the points, we can observe the following remarks. The del operator, which was introduced by the mathematician Hamilton, is defined by del equals I cap dou by dou X plus j cap dou by dou Y plus k cap dou by dou Z. This is a vector differential operator and it is called the gradient operator. The gradient operator applies on a scalar field and it produces a vector field. So, the gradient operator is a vector differential operator which applies on scalar fields and produces vector fields. Whereas the divergence operator del dot is a vector differential operator that applies on vector fields and produce scalar fields. These points are very important to be understood. Let's understand the finding of the divergence of a given vector field by using a few examples. As a first example, let us consider a vector field f from R3 to R3 defined by f of x comma y comma z equals x plus y I cap plus y plus z j cap plus x plus z k cap. As soon as a vector field is given, we need to write its component functions. For this vector field, the component functions are f1 of x comma y comma z equals x plus y, f2 of x comma y comma z equals y plus z, and f3 of x comma y comma z equals x plus z. These are the component functions of the given vector field f. So, the divergence of the given vector field f is the sum of three pieces: dou f1 by dou x, dou f2 by dou y, and dou f3 by dou z. In this example, if we find out the partial derivative of f1 with respect to x, it is dou f1 by dou x equals 1. If we find the partial derivative of f2 of x comma y comma z equals y plus z with respect to y, it is also 1. So, dou f2 by dou y equals 1. Similarly, since f3 of x comma y comma z equals z plus x, its partial derivative with respect to z is also 1. Div f is the sum of these three pieces. So div f equals dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. It gives us 1 plus 1 plus 1 equals 3. So in this example, the divergence of the given vector field f of x comma y comma z is 3. Let us switch over to the second example. In the second example, a vector field g from R3 to R3 is defined by g of x comma y comma z equals x square I cap plus y square j cap plus z square k cap. For this vector field, the component functions are z1 of x comma y comma z equals x square, which is the coefficient of I cap, z2 of x comma y comma z equals y square, which is the coefficient of j cap, g3 of x comma y comma z equals z square, which is the coefficient of k cap. Now we have the component functions z1 equals x square, g2 equals y square, and g3 equals z square in hand. Now we need to compute their partial derivatives. Dou z1 by dou x, dou z2 by dou y, and dou g3 by dou z. The divergence of g is given by dou z1 by dou x plus dou g2 by dou y plus dou g3 by dou z. In this case, dou g1 by dou x equals to x, dou g2 by dou y equals to y, dou g3 by dou z equals to z. The sum of all these three gives us the divergence of z. So div z equals 2x plus 2y plus 2z. Now the third example is r cap equals xi cap plus yj cap plus zk cap, which is our velocity vector. The component functions of this r cap are x, y, and z. So if we find out the partial derivative of the first component with respect to x, we get 1. The partial derivative of the second component with respect to y is also 1. Similarly, dou r3 by dou z, the partial derivative of the third component is also 1. So the divergence of this vector field r cap is dou r1 by dou x plus dou r2 by dou y plus dou r3 by dou z, which equals 1 plus 1 plus 1, that equals 3. So div r cap is also 3. So far, we have learned the definition of the divergence of a vector field, and we have seen a few examples. The divergence of a vector field has so much of physical importance. So let us understand its physical importance. Let us choose a vector field f of x comma y comma z. This vector field can be written as f of x comma y comma z equals f1 I cap plus f2 j cap plus f3 k cap. Actually, it represents a fluid flow, or it may be a electric flow through a circuit. So let us select a position vector on the fluid, say x comma y comma z. Choose a small sphere around this position vector x cap equals x comma y comma z by taking x cap equals x comma y comma z as its center. Now, this divergence of this fluid flow represents the outflow of the fluid per unit volume from this sphere. Actually, if the outflow is larger than the inflow of this fluid, then the divergence of the vector field F is positive. If the inflow is larger than the outflow of the fluid, then div F is negative. We see the next case div F is equal to 0 after some time. Physically, the divergence of a vector field represents the outflow of a fluid per unit volume. It is also called flux per unit volume at the given point P. Flux means outflow.
I hope you are enjoying our lectures. If you prefer any specific topic, please let me know in the comment box. You can write a mail to us for our lecture notes. Please subscribe our channel and press the bell for notifications. If you like the content, spread the word. Thanks for watching.